Hello friends, we have been talking about parallel lines and parallelograms. In particular, we have been talking about parallelograms in between parallel lines. We saw that the parallelograms on the same base and between two parallels are equal in area. This is the theorem that we proved in our last video. Friends, remember that theorems without proof are just mere statements. So, never accept a theorem without proof. So friends, with the help of this theorem, let's solve some problems. So, here is our first problem. In this problem, we have a parallelogram ABCD and a triangle PAB. Now we have to prove that the area of the triangle PAB is half the area of the parallelogram ABCD. We can clearly see that the base of both these figures is the same. And also, both these figures are between the same parallels. Now our aim is to prove that the area of the triangle PAB is half times the area of the parallelogram ABCD. So, what will be the first step? Having trouble? Don't worry. I'll provide you with a small hint. Draw a line segment from point B onto CD such that the line segment is parallel to P and name this point Q. Now we get the parallelogram ABQP. It's time for an observation. Here the parallelograms ABCD and ABQP are on the same base and between the two same parallels, which implies that the area of the parallelogram ABCD is equal to the area of the parallelogram ABQP. Now, in what way does this observation help us? Just wait and watch. We will now recap one specific property of parallelograms. We know that in a parallelogram, a diagonal divides the parallelogram into two triangles of equal area. This property will help us get through this problem. Here, we can see that the area of the parallelogram ABQP is equal to the sum of the areas of the triangles ABP and BQP. Now comes the importance of this property. Here we can clearly see that BP is a diagonal in the parallelogram ABQP. Since BP is a diagonal, from this property we can conclude that the area of the triangle ABP is equal to the area of the triangle BQP. So, the area of ABQP is equal to the area of ABP plus the area of BQP, which is nothing but 2 times the area of ABP, since the area of ABP is equal to the area of BQP. So, we proved that the area of the parallelogram ABQP is 2 times the area of the triangle ABP, which implies that area of the triangle ABP is half times the area of the parallelogram ABQP. We also proved that area of the parallelogram ABQP is same as the area of the parallelogram ABCD, since both of them are on the same base and between the same parallels. So, the area of the triangle ABP is half of the area of the parallelogram ABCD. That's it. We proved the problem. In this problem, what we actually proved is, if there is a triangle and a parallelogram on the same base and between the same parallels, then the area of that triangle is half times the area of that parallelogram. So till now we have made 2 important observations. The first observation is, if there are 2 parallelograms on the same base and between the same parallels, then the areas of the parallelograms are equal. The second observation is, if there is a triangle and a parallelogram on the same base and between the same parallels, then the area of the triangle is half of the area of the parallelogram. Now let's move on to our next problem. In this problem, it has been mentioned that ABCD is a parallelogram and E, F, G, H are the midpoints of the sides of the parallelogram respectively. Now we have to prove that area of EFGH is half of the area of ABCD. So in this problem, we have a parallelogram ABCD and EFGH are the midpoints of the sides of the parallelogram respectively. So let's join EFGH. Now we have to prove that the area of EFGH is half of the area of the parallelogram ABCD. So how will we prove it? What will be the first step? The hint is to join the midpoints H and F. By joining them, we get two triangles HGF and HEF. We will get two parallelograms as well, HDCF and HABF. Since a line joining the midpoints of the sides of the parallelogram will be parallel to the sides of the parallelogram. Now consider the parallelogram HFCD and the triangle HGF. We can clearly see that both of them are on the same base, that is HF, and they are between the same parallels HF and CD. So we can conclude that the area of the triangle HGF is half of the area of the parallelogram HFCD. In the same way, if we consider the parallelogram HABF and the triangle HEF, we can clearly see that both of them are on the same base and also between the same parallels. So we can conclude that the area of the triangle HEF is half of the area of the parallelogram HABF. So we have observed two things. The area of the triangle HGF is half of the area of the parallelogram HFCD. The area of the triangle HEF is half of the area of the parallelogram HABF. Let's just add them up. So we get the area of the triangle HGF plus the area of the triangle HEF is equal to half the area of the parallelogram HFCD plus half the area of the parallelogram HABF. Now from the diagram we can clearly see that the triangles HEF and HGF together form the figure EFGH, and the parallelograms HABF and HFCD together form the parallelogram ABCD. Thus we get area of the shape EFGH is half of the area of the parallelogram ABCD. That's it. We proved that area of the shape EFGH is half of the area of the parallelogram ABCD. From this problem, what we can understand is, if we form a quadrilateral by joining the midpoints of the sides of a parallelogram, then the area of the quadrilateral formed will be half of the area of that parallelogram. So friends, that's all for today. Before we end the video, I urge you to remember these observations very carefully because they'll help us a lot in solving the problems. In our next video, let's meet with a new concept. Till then, stay tuned.